Welcome to the Physics and Cosmos Academy, where we explore cutting-edge discoveries pushing the frontiers of science.
When we gaze up at the night sky, we are met with a breathtaking tapestry of stars, planets, and distant galaxies. The universe appears to us as a vast and luminous expanse, but what we see is just a tiny fraction of what's really out there. Hidden from our view lies an invisible universe, a realm of particles and forces that shape the cosmos in ways we are only beginning to understand. Neutrinos are truly enigmatic particles. They possess no electric charge, meaning they are unaffected by electromagnetic forces that govern the interactions of everyday matter. Their mass is incredibly tiny, almost non-existent, making them incredibly difficult to detect. Imagine a tiny subatomic ghost zipping through the cosmos at nearly the speed of light. That's a neutrino. They are so weakly interacting that they can travel through light years of lead without being stopped. Our planet, our bodies, even the densest stars are no obstacle to these ethereal travelers.
In recent years, scientists have made remarkable strides in detecting and studying neutrinos. Using sophisticated detectors buried deep underground or submerged in the depths of the ocean, we have begun to unravel some of the secrets these ghostly particles hold. One such discovery has sent ripples of excitement through the scientific community. In the depths of the Mediterranean Sea, the KM3NeT Observatory, a massive neutrino telescope, detected a neutrino with an unprecedented energy level, far exceeding anything observed before.
The search for neutrinos is a challenging endeavor. Their weak interaction with matter makes them incredibly difficult to detect. To catch these ghostly particles, scientists have built enormous detectors, often located in extreme environments to shield them from cosmic rays and other interfering particles. One such detector is the KM3NeT Observatory, a grid of thousands of sensitive light sensors submerged in the depths of the Mediterranean Sea. The vastness of the ocean provides a natural shield against cosmic rays, while the darkness of the abyss allows the faint signals of neutrino interactions to be detected. Neutrinos are among the most abundant particles in the universe, yet they remain shrouded in mystery. They are fundamental particles, meaning they are not made up of smaller constituents. They belong to a family of particles called leptons, which includes the familiar electron but also its heavier cousins, the muon and the tau. What sets neutrinos apart is their ghostly nature. They carry no electric charge, which means they are unaffected by the electromagnetic force, the force responsible for most of the interactions we observe in the everyday world. Light is an electromagnetic wave, and we see because our eyes detect this light. Neutrinos, however, pass right through our eyes, our bodies, and even the entire Earth without leaving a trace.
Neutrinos are produced in a variety of astrophysical processes, from the relatively benign nuclear reactions in the cores of stars to the most cataclysmic events in the universe. The vast majority of neutrinos that reach Earth come from the Sun, born in the fusion reactions that convert hydrogen into helium, releasing the energy that sustains life on our planet. But neutrinos are also produced in more extreme environments. When massive stars reach the end of their lives, they explode as supernovae, releasing a burst of neutrinos so intense that it briefly outshines the entire galaxy. These supernova neutrinos carry with them information about the processes that occur in the final moments of a star's life.
The Standard Model of Particle Physics, our best current understanding of the fundamental building blocks of matter and the forces that govern their interactions, describes three types or flavors of neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino. Each flavor of neutrino is associated with its corresponding charged lepton, the electron, muon, and tau, respectively. But neutrinos have a peculiar property that makes them even more fascinating. They can oscillate between flavors as they travel through space. This means that an electron neutrino produced in the Sun, for example, could transform into a muon neutrino or a tau neutrino by the time it reaches Earth. The fact that neutrinos have mass, even if it is incredibly small, has significant consequences for our understanding of the universe. In the Standard Model, neutrinos are assumed to be massless, but the observation of neutrino oscillation requires that they have at least a small amount of mass. The exact mass of neutrinos is still unknown, but scientists are working hard to determine it. The challenge lies in the fact that neutrinos interact so weakly with matter, making it extremely difficult to measure their properties directly. Neutrinos, with their ability to travel through the universe unimpeded, offer us a unique window into the most extreme environments in the cosmos. They can escape from the cores of collapsing stars, from the vicinity of black holes, and even from the early universe, carrying with them information that would be impossible to obtain any other way. By studying the energy, direction, and flavor of neutrinos arriving at Earth, astrophysicists can learn about the processes that produce these particles and the environments in which they originate. The study of neutrinos is a rapidly evolving field, with new discoveries being made all the time. As we build more sensitive detectors and develop new techniques for studying these elusive particles, we can expect to unlock even more secrets about the universe. The detection of the record-breaking high-energy neutrino by the KM3NeT observatory is just the latest example of the exciting discoveries that await us in the realm of neutrino astronomy.
Imagine trying to hear a whisper in the midst of a hurricane. That's the challenge facing scientists trying to detect neutrinos from the cosmos. Our planet is constantly bombarded by a cacophony of particles, from cosmic rays to radioactive decay products, creating a noisy background that can drown out the faint signals of these ghostly messengers. To isolate these subtle whispers from the cosmic roar, scientists have turned to some of the most remote and extreme environments on Earth. Deep underground laboratories, shielded by kilometers of rock, offer refuge from the relentless bombardment of cosmic rays. But another, even more challenging environment holds even greater promise: the deep ocean.
Cosmic rays, those high-energy particles constantly raining down on Earth from space, pose a significant challenge to neutrino detection. These particles interact with the Earth's atmosphere, creating showers of secondary particles that can mimic the signals produced by neutrinos. Shielding from cosmic rays is crucial for any neutrino detector, and this is where the ocean truly shines. Water, with its density and sheer volume, acts as an incredibly effective shield against these cosmic interlopers. As cosmic rays enter the water, they collide with water molecules, losing energy and producing a cascade of secondary particles.
Imagine a telescope, not pointed at the sky, but submerged in the deepest, darkest depths of the ocean. Instead of mirrors and lenses, it uses thousands of sensitive light sensors, spread out over a cubic kilometer of seawater, to capture the faintest glimmers of light produced by neutrino interactions. This is KM3NeT, the cubic kilometer neutrino telescope. KM3NeT is not a single monolithic structure, but rather a distributed network of detector modules, strategically positioned on the seabed. Each module consists of a pressure-resistant sphere, containing highly sensitive light detectors called photomultiplier tubes, arranged to capture light from all directions. Building a scientific instrument of KM3NeT's scale and complexity, and deploying it in the harsh environment of the deep ocean, is a monumental engineering challenge. Every component, from the sensitive light detectors to the pressure-resistant housings, must be designed to withstand the immense pressure, the corrosive seawater, and the challenges of operating in near-total darkness. The detector modules themselves are marvels of engineering. Each sphere is made of a special glass, carefully chosen for its transparency and strength, able to withstand the crushing pressure at a depth of several kilometers. Inside each sphere, the photomultiplier tubes are housed in a carefully designed support structure, protecting them from shocks and vibrations.
KM3NeT's ability to detect neutrinos relies on a phenomenon known as Cherenkov radiation. This eerie blue glow is produced when a charged particle, such as an electron or a muon, travels through a medium, such as water, faster than the speed of light in that medium. When a neutrino interacts with an atom in the vicinity of the detector, it can produce a charged particle, such as a muon. This muon, carrying some of the original neutrino's energy, continues to travel through the water, and if its speed exceeds the speed of light in water, it emits Cherenkov radiation. Imagine being submerged in the abyssal depths, surrounded by the crushing pressure and the inky blackness of the ocean. Suddenly, a faint blue glow, a fleeting flash of light, dances across your field of view. This ethereal glow, known as Cherenkov radiation, is the telltale sign of a neutrino's passage, a whisper of energy from the distant cosmos. This is the world in which KM3NeT operates, a world where the faintest flickers of light carry profound secrets about the universe. The detector modules, scattered across the seabed like luminous pearls, stand ready to capture these fleeting flashes, their sensitive photomultiplier tubes poised to convert these whispers of light into measurable signals. The Cherenkov light emitted by a muon as it traverses the KM3NeT detector array is incredibly faint and fleeting, lasting for only a few billionths of a second. Capturing these ephemeral flashes of light requires exquisite timing and sensitivity, pushing the limits of modern electronics and data acquisition systems. Each photomultiplier tube in the KM3NeT detector modules is a marvel of engineering capable of detecting even single photons of light. When a photon strikes the photocathode of the tube, it knocks loose an electron, which is then amplified through a series of diodes, creating a measurable electrical pulse. Imagine trying to determine the location of a lightning strike by analyzing the sound of thunder as it reaches different points on the ground. This, in essence, is the challenge facing KM3NeT scientists as they attempt to pinpoint the origin of neutrinos arriving from deep space. Just as the sound of thunder arrives at different times at different locations, the Cherenkov light emitted by a muon reaches different KM3NeT detector modules at slightly different times, depending on the muon's trajectory and the relative positions of the modules. The KM3NeT detector array, with its thousands of photomultiplier tubes spread out over a cubic kilometer of seawater, generates an immense amount of data, a torrent of information that must be carefully processed and analyzed to extract the faint signals of neutrino interactions. Every second, the detector modules record millions of events, most of which are caused by background noise, such as the radioactive decay of naturally occurring isotopes in the seawater, or bioluminescence from marine organisms. Sifting through this data deluge to find the few precious events caused by neutrinos is a daunting task.
The KM3NeT project, with its scale, complexity, and scientific ambition, is a testament to the power of international collaboration. Scientists and engineers from more than 40 institutions in 13 countries have come together to design, build, and operate this unique scientific instrument. The challenges of building a neutrino telescope in the deep ocean, from designing and deploying the detector modules to managing the massive data flow, have required expertise from a wide range of disciplines including particle physics, astrophysics, oceanography, and computer science.
Deep beneath the surface of the Mediterranean Sea, in the silent embrace of the abyssal plain, the KM3NeT observatory stands vigilant, its thousands of sensitive eyes peering into the darkness, searching for the faintest glimmer of light that would betray the passage of a ghostly cosmic messenger. For months, the detector had been patiently collecting data, its photomultiplier tubes recording the random flashes and flickers of background radiation, the constant hum of the abyss. Then, on February 13, 2023, a signal emerged from the noise, a pattern of light unlike anything seen before. The detection of a single muon in the KM3NeT detector is, in itself, not an unusual occurrence. Muons, produced by the interaction of cosmic rays with the Earth's atmosphere, are a constant presence, raining down on the planet from all directions. What set this event apart was the muon's extraordinary energy and its upward trajectory. This muon, the scientists realized, had not originated in the atmosphere above, but had instead traveled through the entire Earth, passing through thousands of kilometers of rock and water before leaving its telltale signature in the KM3NeT detector. The detection of a neutrino with such an extraordinary energy level sent shock waves through the scientific community. It confirmed what many had long suspected, that the universe harbors cosmic accelerators capable of generating particles with energies far beyond anything we can achieve on Earth. These cosmic accelerators, the scientists believe, are most likely powered by the most extreme objects in the universe: supermassive black holes at the centers of galaxies, active galactic nuclei spewing out jets of high-energy particles, or perhaps even the remnants of supernova explosions, the fiery death throes of massive stars. Having detected the ultra-high-energy neutrino, the KM3NeT scientists faced a new challenge. Could they trace it back to its source, identifying the cosmic accelerator that had flung this tiny messenger across the vastness of space? Neutrinos, unlike light or charged particles, travel through the universe in essentially straight lines, undeflected by magnetic fields and virtually unimpeded by matter. This makes them ideal cosmic messengers, carrying with them a clear record of their journey from their point of origin.
The detection of the record-breaking high-energy neutrino by KM3NeT marks a pivotal moment in the nascent field of neutrino astronomy. It has opened a new window on the universe, allowing us to observe the cosmos in a way never before possible. Neutrinos, with their ability to escape from the densest and most extreme environments in the universe, offer a unique perspective on the cosmos, providing information that is inaccessible through any other means. They are the ultimate cosmic messengers, carrying with them secrets from the hearts of stars, the edges of black holes, and the earliest moments of the universe.
The detection of the ultra-high energy neutrino by KM3NeT has presented scientists with a tantalizing mystery. What celestial object or event could have generated a particle with such immense energy? This single neutrino acts as a messenger from the most extreme environments in the universe, hinting at the existence of cosmic accelerators that dwarf anything we can create on Earth. Astrophysicists have long theorized about the existence of these natural particle accelerators, objects capable of accelerating particles to energies far surpassing those achieved by the Large Hadron Collider, the most powerful particle accelerator ever built by humans. These cosmic accelerators are thought to be powered by the immense gravitational forces of black holes, the explosive energy of supernovae, or the powerful magnetic fields of pulsars. The study of neutrinos, with their elusive nature and extreme energies, has the potential to push the boundaries of our understanding of particle physics, perhaps even revealing clues about physics beyond the Standard Model. The Standard Model, our current best description of the fundamental particles and forces that govern the universe, has been incredibly successful in explaining a wide range of phenomena. However, there are some mysteries that the Standard Model cannot explain, such as the existence of dark matter and dark energy, the nature of gravity, and the masses of neutrinos themselves. Neutrinos, according to the Standard Model, should be massless. However, the observation of neutrino oscillations, the ability of neutrinos to change flavor as they travel through space, has definitively proven that they must have a small, albeit non-zero mass.
The detection of the record-breaking neutrino by KM3NeT is a triumph not only for neutrino astronomy, but also for the burgeoning field of multi-messenger astronomy. For centuries, astronomers relied solely on light in its various forms to study the cosmos. However, the universe speaks to us in many languages through a symphony of messengers that carry information about the most energetic events in the cosmos. These messengers include not only neutrinos but also cosmic rays, high-energy particles that bombard Earth from space, gamma rays, the most energetic form of light, and gravitational waves, ripples in the fabric of space-time itself. Each of these messengers carries unique information about the objects and events that produce them.
The detection of the ultra-high energy neutrino by KM3NeT is just the beginning of a new era of neutrino astronomy. As neutrino telescopes become larger, more sensitive, and more sophisticated, we can expect a steady stream of discoveries, each one revealing a little more about the hidden workings of the universe. KM3NeT itself is still under construction, with plans to expand its size and sensitivity in the coming years. Other neutrino telescopes are also under development, including IceCube Gen 2, a planned expansion of the IceCube Neutrino Observatory, located at the South Pole, and the Giant Radio Array for Neutrino Detection, or GRAND, an ambitious project that aims to use an array of radio antennas spread across a vast area to detect ultra-high energy neutrinos.
The detection of the ultra-high energy neutrino by KM3NeT is a testament to the power of human curiosity, our insatiable desire to explore the unknown and unravel the mysteries of the universe. It is a reminder that the universe is full of surprises, that there is always more to learn, and that even the most elusive and ghostly of particles can hold the keys to unlocking profound secrets about the cosmos. For centuries, we have gazed up at the night sky and wondered at the vastness and complexity of the universe. But it is only in recent decades that we have begun to develop the tools and techniques needed to explore the universe beyond the realm of visible light, to peer into the heart of stars, to witness the collisions of black holes, and to catch fleeting glimpses of the most elusive particles in existence. The detection of the record-breaking high-energy neutrino by KM3NeT stands as a testament to the remarkable progress we've made in our quest to understand the universe. It marks a pivotal moment in the nascent field of neutrino astronomy, offering us a new lens through which to observe the cosmos, one that allows us to peer into the heart of the most extreme environments, where the laws of physics are pushed to their limits. For centuries, our understanding of the universe was limited to what we could see with our own eyes or through telescopes that captured the faintest glimmers of visible light. But the universe speaks to us in many languages, through whispers of energy and matter that elude our ordinary senses. Neutrinos, those ghostly particles that barely interact with matter, are among the most fascinating and enigmatic of these cosmic messengers.
The KM3NeT Observatory, a marvel of engineering and a testament to international collaboration, stands as a beacon of human ingenuity, a symbol of our relentless pursuit of knowledge and our determination to push the boundaries of human understanding. Building a neutrino telescope of this scale and complexity, deploying it in the harsh environment of the deep ocean, and extracting meaningful data from the deluge of information it collects is a feat that would have been unimaginable just a few decades ago. It's a testament to the dedication and ingenuity of the hundreds of scientists, engineers, technicians, and support staff from around the world who have contributed to this remarkable project. Their combined efforts, spanning decades of research and development, have culminated in an instrument of unprecedented sensitivity, capable of detecting the faintest whispers of energy from the distant cosmos.
The detection of the ultra-high-energy neutrino by KM3NeT is just the beginning of a new era of discovery, a glimpse into a universe teeming with unseen wonders, a cosmos far more vast and intricate than we could have ever imagined. As we continue to explore the cosmos, using ever more sophisticated instruments and techniques, we can expect to uncover even more astonishing secrets, each one challenging our understanding of the universe and pushing the boundaries of human knowledge. Neutrino astronomy, with its ability to probe the most extreme environments in the universe, is still in its infancy. But as neutrino telescopes become larger, more sensitive, and more sophisticated, they promise to revolutionize our understanding of the cosmos, unveiling a universe of wonder and discovery that we are only beginning to imagine. The cosmos, with its vastness and complexity, its elegance and mystery, has captivated the human imagination for millennia. From the earliest stargazers who looked up in awe at the night sky to the modern astronomers who probe the depths of the universe with sophisticated instruments, we have always been driven by a deep-seated desire to understand our place in the cosmos, to unravel the secrets of the universe, and to grasp the fundamental laws that govern its workings. The detection of the record-breaking high-energy neutrino by KM3NeT is a testament to our insatiable curiosity, our relentless pursuit of knowledge, and our ability to overcome seemingly insurmountable challenges in our quest to explore the unknown. It's a reminder that the universe is full of surprises, that there is always more to learn, and that even the most elusive and ghostly of particles can hold the keys to unlocking profound secrets about the cosmos.
Thank you for joining us on the Physics and Cosmos Academy. If you enjoyed this in-depth look at the latest discovery in neutrino astronomy, please remember to like, comment, and subscribe, so you won't miss our future explorations of the cosmos.